Welcome. My name is Lanyue. I'm happy to present our project, a study of Linux file system evolution. And this is a joint work with professors Andrea and Remzi, Arpaci-Dusseau, and Shan. Local file systems are critical in modern storage systems. You know that when you use your desktop and laptop, no matter you use Windows, Mac, or Linux, your data is managed by local file systems. In cloud data centers, local file systems are also the backbone of large-scale distributed file systems. Google GFS, Hadoop DFS, they both replicate data and metadata across local file systems. They are even on the phones. Android devices use Ext4, iPhone use HFX. So local file systems store your data. That's why we want to study more about local file systems. In general, study drive system designs. Most previous work focuses on measurements, but there are little emphasis on system evolution. A study of Linux file system evolution is very important, very useful to answer many important questions. For example, where does the complexity of file system lies? What kind of performance techniques they use? Is there any similarity across different file systems? Such a study is also useful for multiple communities. For file system developers, you can read all these previous bug patterns to avoid to make same mistakes. You also can improve your current existing design and implementation by borrowing popular performance and reliability enhancements. It's also very useful for system researchers. Our study can help you to identify real problems that plague existing systems and match your research to realities. Our study contains a large scale of bug patterns, bug consequences. These statistics can be used by tool builders to build very useful tools. File systems are not static. The code base involved by adding new features, fixing existing bugs, improving the performance and reliability. Patches exactly describe how one version of kernel transforms to next versions. And each patch for open source file systems are available online. And this enables us to analyze file systems in great detail. So system archaeology is now possible. And we also started with other rich informations. What we did in this project is our study is based on manual patch inspections. We studied 6 file systems. We included all the patches in the Linux 2.6 series. There are a total 5,000 patches, and we analyzed them multiple times. Once we are done, we can turn our manual analysis into annotated data sets. This enables us to quantitatively analyze file systems in many aspects. For example, you can ask what kind of patch they have, what kind of resource leak they have in different file systems, where the file system check their metadata corruptions. And we also provide an annotated data set for you. You can look further for different analysis. So now let's preview our major results briefly. We found that bugs are prevalent in both young and old file systems. Among all these bugs, semantic bugs dominate. The number of bugs doesn't die down over time, but rather is constant in a file system lifetime. Data corruption and system crash are the most common bug consequences. Metadata management is complex and has high bug density. Failure paths are particularly error-prone in file systems. And a wide variety of same performance techniques are used across different file systems. Next, I will describe our methodology and present some interesting results. We choose a diverse set of file systems. They are developed by different groups of people. They use different techniques. We include all the patches in Linux 2.3 kernels. This version spans 8 years of time. The total have 5,079 patches. Usually, a patch usually contains clear description of its purpose and also rich diagnostic information. A patch has 3 parts: header, description, body, and related code. Now let's look at a very simple Ext3 patch. From the header, we can know that this patch is used to fix a null pointer bug in Ext3. From the description body, we can know the location and the cause of the bug. And it also mentioned this bug was detected by cooperative tools. This is the related code. From the code, we can find at line 1, they check whether the pointer is null or not. Even if it's null, it's still dereferencing at line 5. So a very simple fix is add a return null in this place. So for each patch, we analyze them in multiple perspectives. In terms of patch overview, we analyze their patch type, their patch size. For previous example, the patch is a bug patch. The size is 1. For bugs, we do further analysis, such as bug pattern, bug consequence, related data structures, and what tools are used. Previous example is a memory bug. It caused system crash. It's related to super block. It's detected by cooperative. If a patch is performance or reliability patch, we also do similar pattern and location analysis. There are a few limitations in our study. We only studied 60 popular file systems. There are many others in Linux. And we only studied Linux 2.6 kernels. We omit earlier versions. And we only studied reported bugs. There probably had many existing but unknown bugs. Now I present our study results. Here is a list of key questions we want to answer in our study. What do file system patches do? What their bugs looks like? Does the number of bugs diminish over time? What consequences they will cause? Where the complexity lies? Do bugs occur on normal paths or failure paths? And what popular performance techniques they use? Question 1, what do patches do? We partition file system patch in 5 categories: fixing existing bug, improve performance, improve robustness, add a new feature, maintain the code. For all this, in this talk, I will show many bar graphs. All these graphs have similar structures. On the x-axis, I show different number of file systems ordered by from XFS to JFS. At the end of x-axis, we have an OR notation that represents aggregation of all file systems. Y-axis shows the percentage of different types. At the top, we show the number of patches for each file system. For example, for XFS, in total, it has 2,004 patches. And all the file systems have 5,079 patches. First, we show the percentage of bug patch. We can see that the bug patch has a significant presence, account around 40%. BartFS is a new file system, so it has a larger percentage. But even for stable and mature file systems such as the Ext3, still have a sizable percentage. And we'll look more bugs in later. Performance and reliability patch account for 8% and 7% respectively. And they only have a small amount of feature patch, but most of feature patch contains more lines of code compared with other type of patch. And the maintenance patch has a huge percentage across all the file systems. And this patch usually is like simplify the code structures, use the new API, and also maintain the documentations. So maintenance is a huge category, and this usually represents the necessary cost to maintain a large and complex system in open source systems. But they are not relatively interesting, so we will not look further them anymore. The bug patch is the second largest percentage, and this is achieved for both stable and new file systems, and we will show more examples of them. The second question is, what do file system bugs look like? There are 4 types of bugs in the file system: semantic bugs, incorrect concurrent behavior, incorrect handling of memory objects, and miss or wrong error code handling. I will show examples of each category. First, let's look at semantic bugs. When Ext3 wants to allocate an inode, it will scan from parent group and scan all the candidate block group. In line 1, it starts from a wrong block group, and in line 2, it omits 2 block groups. So the correct implementation is start from the parent group and scan all candidate block group. And this is a semantic bug. A possible consequence is even you have free inodes, but original Ext3 they cannot find them. They will return a no space error. Among bugs, we found semantic bugs dominate other types of bugs. Over half of them are semantic bugs, And this is true over all the file systems. And very few tools can help to detect semantic bug in file systems. Most previous studies focus on concurrency, memory, and error code bugs. Most existing tools focus on concurrency, memory, and error code bugs. But we found a huge percentage of semantic bugs in file systems. And we also have like nearly 18,000 bugs across all the file systems. And this provides a great opportunity for people to look at their patterns in large scale. Now let's look at a concurrency bug examples. In here, when two CPU simultaneously allocate blocks, there is no protection for the I-catch extents. So the consequence is you may cause a wrong location on disk to read or written. So a simple fix is use a spin lock to protect these protections. So this is a typical concurrency bug. Concurrency bugs also have a huge percentage, around 20% across all the file systems. Let's look at a very simple memory bugs. In here, BartFS allocated an inode at line 1, but it forgets to free them when some error happens. So a simple fix is free the inode before you return error code. Memory bug account 10%. Many commercial and research tools are proposed to detect memory bugs. And we found actually in file systems that many developers, they really use this tool to find them. Lastly, let's look at an error code example. In readFS, in line 1, this function possibly can return error code to ACL, but it didn't check error code, and it just directly dereferenced them at line 2. So a possible crash can happen. So a simple fix is you check the error before you dereference them. And error code accounts for remaining 10%. So we can see that over half of the file system bugs are semantic bugs. And these semantic bugs usually require file system knowledge to understand, to detect, and to fix. And we argue that more attention to need in this area. The next question we want to ask is, do file system bugs diminish over time? Let's look at how Ext3 Bug Trend over these 40 versions. So the x-axis we show the 40 version of this kernel. On y-axis we show the number of bugs at each version. At 2.6.10 and 2.6.11, there are 2 new features added. Then they have a search of the bug patch related to these 2 new features added. Simulation happens at 2.6.17 when Ext3 added a multiple block allocation algorithm. There are multiple patches to fix the bug. It's happening there. At 2.6.38, Ext3 also fixed multiple missing error handling bugs. Now let's look at all the file systems together. In this graph, all these x-axis show the different version, kernel version number, and the y-axis shows the number of bugs at each versions. Overall, we find that the number of the bugs doesn't die down over time, no matter for new file system or old file systems. A great example is XFS. It's a stable file system in the Ext2 2.4, but even in Linux 2.6, the number of bugs still decline and regrow in cycles. For new file system, Ext4 and BartFS have a huge increase of bug patch at the beginning of the lifetime. And for readFS and the JFS, they have smaller number of developer and user communities. And we found that JFS does decline, not bug patch within time. And some exception also occurred. We found that the readFS has a huge spike at 2.6.13. Then we break down all these bugs in different types. We found a huge percentage of concurrency bugs happen there. The reason is readFS want to remove big kernel lock, and that introduced a lot of lock violation. That's why they have a huge spike of concurrency bugs there. So bug fixing is a constant in a file system lifetime. They are ebbing and flowing over in cycles. Then we ask whether this bug will cause serious consequence or not. There are several types of consequences: data corruption, system crash, unexpected errors, deadlock, system hang, resource leak, and wrong behavior. Now we will look at all of them. First, we can find that data corruption is the most dominant type of bug consequence across all the file systems, nearly 40%. System crash also happen very frequently, take about 20%. And most of the crash is because of triggered by internal assertions or null pointer dereferences. Unexpected error and deadlock also happen pretty frequently. System hang and resource leak happen less frequently. And finally, a small part of wrong behavior happens in the file system. And this has a huge difference compared with the user-level applications, where wrong behavior is their dominant types. So file system bugs are pretty serious. They cause data corruption and crash, and this happens very often. Next question we ask is, does each logic component of file system have the same degree of complexity? File systems usually have similar data structure and design. We partitioned each file system in these 9 components: the block allocation, directory management, extend management, file operations, inode metadata, transaction code, civil block metadata, tree structures, and other components. For this, now we study the correlation between the code and the bugs. Each graph represents a different file systems. All these x-axis show the percentage of the code of each component. And the y-axis will show the percentage of bug of each component. If a point is above the line, that means that component has a higher bug density than expected. If a point under the line, that means it has a relatively fewer number of bugs. First, we found that for file, inode, and civil block components, for all the file systems, these 3 components are above the line. That means they contain disproportional bugs than they expected. For file components, most of the bug is due to the f-sync path or custom I/O operations. For inode and civil block, the major file system metadata structure maintain a lot of information in the file systems, and they are widely accessed and updated in different places. And it's usually very easy to make an error to forget the updates or update them in your wrong place. Next, let's look at the transactional code. Transactions usually account a large percentage of code, and their bug density is also proportional. So transaction code is like a double-edged sword in the file system. They were proposed to improve data consistency, but they also introduce a large amount of bugs because of their complexity and large code base. We are surprised to find the tree structure actually has a very small amount of bugs compared with their code percentage. The reason probably is because the B tree is well understood and widely used in database areas. For the remaining components, there are no general trend. It depends on each file system design. So metadata management is pretty complex and usually can cause a lot of bugs. And most of them are related to semantic bugs, like you incorrectly update your file system states. And bookkeeping metadata is not an easy job. It's very easy to get wrong. And tree-related code is not particularly error-prone. Next question we ask is, do file system bugs occur on normal paths or failure paths? File systems have to handle a wide range of failures, like resource allocation, silent data corruption, I/O failures. And they have unique code styles. They use a lot of good statements once error happens. They use error code propagation from low level to high level. Let's look at several examples. Here is a semantic bug on failure paths. When Ext3 detected multiple reciters run at the same time, they just return error code and go to exit. But it forgot to mark a journal as abort. So they didn't prevent further corruption happens. Here is a memory bug on failure paths. When Ext3 found that inode is corrupted, it directly goes to the inode function. But it forgot to free some buffer head used to read the inode. So here is the percentage of bugs happen on failure paths across all the file systems. So we can find around 40% of bugs in file systems happen on failure paths. And this is a huge percentage. And in our paper, we have further analysis of different types of bugs that happen in there and what their pattern looks like. And we also provide a strong motivation to correct them in the first place. The last question, we switch gear to performance perspective. What performance techniques are used in different file systems? We have several categories like improve synchronization efficiency, apply smart access strategy, scheduling I/O operation, have better scalability, better locality, and other parts. Let's look at a synchronization example. When Ext3 they want to walk the extended structure to gather extended information, it uses write semicolon to protect them. But because there are no update operation, so a better version is use read semicolon, can improve the concurrency. So for the synchronization-based performance techniques, account about 1/4% of the total performance patch. Here is the access optimization example. When BART-FS want to allocate a cluster of a block, before searching the block group, it first checks whether this block group has minimal number of the free space available. If not, then you can just directly return. You don't need to do all this searching. So this is the access optimization example. It also accounts for 1/4 of the performance patch. I/O scheduling also popular, including batching writes, read ahead, removing unnecessary or ordering, and scalability and locality and the other parts. So a wide variety of same performance techniques are used in different file systems. Now I present our result summary. We found that bugs are prevalent in both young and old file systems. The number of bugs do not die down over time. Among all these bugs, semantic bugs dominates. Data corruption and system crash are the most common bug consequence. Metadata management is pretty complex and error-prone. There are a huge number of bugs happen on failure paths, and a diverse of performance techniques are used across different file systems. Beyond the results, we also want to share with you several lessons we learned across this project. A large-scale study is feasible and valuable. Yes, it definitely is pretty time-consuming, but as a grad student, such is my life. It took us 1.5 years to finish this project, so it is still manageable. And a similar study probably is also interesting for other OS components, such as virtual memory systems. Details matters. We found many interesting and important details, and these details can enable or inspire new research opportunities. For example, once you know how file systems leak their resource, you can build a specialized tool to detect them more effectively. Research also should match reality. New tools are highly desired for semantic bugs. More attention also required to make failure paths correct. Finally, history will repeat itself. We found many similar mistakes happen again and again within and across different file systems. We should pay more attention to system histories, learn from them, build a correct, high performance, and robust file system from the beginning. There are more data in our paper, even more data in our data sets. We spend a lot of time and efforts in this study, so we are happy to share our data set. You can use our data set for your further research or build new tools, or even you just want to learn more about file systems. With that, I take questions.
Akshat Aranya, NEC Labs. I wanted to know if you looked at how the feature patches relate to the bug patches, because it seems like most of the file systems kind of have a lot of bugs coming up right after features are put in. So some correlation between lines of code put in for features and how it relates to how many bugs are found with it.
Yeah, usually when you add a new feature, we observe already, like we show in the talk, there are many following patches for that. But usually it's pretty hard to relate one bug patch to one feature because the code is always overlapping over time. So feature and bug fixing the code over time. So it's pretty hard for us to isolate them. So yeah, it's very interesting if we have the data, but it's also very challenging.
Well, more so like you know that a big feature patch, 200 lines of code went in, and then you saw a surge in bugs coming up related to that, something of that sort.
We didn't analyze the lines of code for feature and related bug patch. Yeah, that's a good point.
Okay, thank you.
Margot Seltzer from Harvard and Oracle. So thank you for doing this study. I can only imagine how much work it is, and the data is fascinating. So my question is sort of like the other one. Those 45% of maintenance fixes that you said were uninteresting, I'm really curious how much analysis you did before deciding they were uninteresting, because one could imagine that people go in to, quote, clean up the code a bit and either A, introduce bugs, or B, fix bugs we didn't know about. And I guess I'm wondering if you did any analysis to decide that there really wasn't anything more complex going on.
That's a very good point. Actually, we found that file system maintainer actually spend a lot of effort to just simplify the code structures, like refactoring the code. Sometimes they definitely introduce bug, but it's hard for us to relate a bug patch to a maintenance code. We didn't do that kind of analysis.
So I'll apologize for asking a very similar question, but have you considered tracing the bugs back to the open source developer who introduced them? If you're laughing, I'm talking about you.
Probably it can do, but it's also very offensive. So.
Hi, Rick Spillane from Apple. So I had a doubt about, in all of your graphs, you compare different file systems. You will average their numbers, like the total number of patches or percentages, and report these aggregate numbers. How did you control for testing frequency and popularity differences between different file systems?
Actually, we choose 6 file systems. Actually, they have different kind of popularity, different kind of stage of development. We didn't specifically relate that to this, but we want to provide a diverse set to represent different file systems. And actually, we found that even they're diverse, but their pattern actually pretty similar across file systems.
Thank you.
My name is Sudarshan Piduri. I'm from VMware. I'm wondering if you have done any study about what percentage of these bugs are because of regressions, like fixing a bug introduces another bug.
Yeah, that's good. Actually, we have data in our data sets. Some bugs they fix the first time, but sometimes another verify, okay, the original fix is wrong. They have to revert to original versions. This happens, and I show here fix on fix is this type of bugs happening, and we have them in our data sets.
Oh, thank you.
Okay, thank you.